Let me start this program by thanking everybody first for coming in. And one of the things we're going to do here is we're going to be taking a different type of approach to some of the information. All of us have made presentations over the years on fundamentals. This one's a little different in that we're going to move forward with what we're thinking of where your future is and some of the trend lines. We're going to core a lot of that information in some of the history, but what we want to do is, and this is the thing I got to ask you to understand, this is a very tight session by timeline. So normally I always allow the audience to do the same thing my wife always abuses me, and that is she will interrupt me at will. So I'm going to ask you guys as a courtesy if you'll hold your Q&A side onto the back side. This way I think we can cover a lot. Let's get rid of that. And then we can find that I think you'll have a much better information feed. And as we get into Q&A, please do not hesitate to be bashful because there's a lot of good data being supported here. So let me start with this. Number one, Shake, Rattle, and Roll 2.0. Dan and I did the original a couple years back. It was very well received, but we're moving it to another level. But before I start, I'd like to introduce Dan Begle and Kevin Feeney. So Dan, I'd like you to start out with a little background.
Well, first of all, thanks everybody for coming. I know the show's super cool. There's so much to learn out there. Appreciate you guys taking your time. It means a lot to us to see you guys here and the interest, and it kind of fuels our fire too. My background, prior to coming to work at Molly, I'm the technical sales engineer at Molly. I work on new products, take care of a lot of performance engine shops, race teams, and make sure they have parts. Before I came to Molly, I did 27 years in NASCAR engines. The last 13 years, I was the reliability engineer at Roush Yates. So my job was to evaluate parts, look at failures, diagnose failure modes, and to create better parts to make the two-race engine that we currently use today. So that was my background. I've been racing all my life, and it's my passion, my hobby, it's my life. So it's fun. Appreciate getting to share with you guys.
Kevin?
My name is Kevin Feeney. I'm the president of P1 Manufacturing. We're a manufacturer of critical engine fasteners in Springfield, Missouri. My background is I spent 20 years with Comp Cam's Comp Performance Group, and then in its latter years, the Edelbrock Group. Oversaw manufacturing. Prior to that, I spent 12 years with Dart cylinder heads in the early days in the development of world products. So I've always been on the fastener side of things, but the consumer, for rod bolts and main studs and head studs, and now being on the other side of the equation has been quite an education, and really exciting, and excited to be able to share some information with everybody here. Thank you.
Okay, now my job is just to make these guys look good, so I'm going to do my best at that. So here's what we're going to do. We're going to start our presentation simply with understanding you guys have a whole different array of background. You all have different resources for making power. In fact, we've evolved to the point in the industry where we're making so much power that we're putting all of the mechanical components into high stress. So we're taking what was started out as pretty much an OEM platform, and then we evolved that into some of these excessive power making. So when I grew up, 500 horsepower was king, boring by today's standards, right? So 1,000, pretty easy. I can go to any of the catalog stores and I can buy all the components and make 1,000 horsepower real quick. But the key here is we'd like for it to live. That's the biggest issue. And that's what we're starting to say. So we're making power, which I'm going to use the word stress, is being generated on a mechanical component that it works till it doesn't. The problem is when it doesn't, it's probably expensive and not pretty. So just real quickly, you can see we have different ways of making power. As we go through this, we have this guy. Now this is the ultimate stress test. And if anything that we have then collectively that makes more power than the applications, whether it's funny car, top fuel, it's absolutely amazing. One of the things that's interesting about it though, is it does have an entertainment factor. All right, now that's not the goal here. The goal here is to have good power, and oh, by the way, I'm going to keep it simple. All of us are in business here, and we need to make money. Well, your reputation for blowing things up is short-lived. Entertaining at best, but I guarantee it's not the best program for your business. So what we want to do is start with this. I want you to observe that and just sort of take a peek which one of those is right and which one is wrong. Now, they're all right. It depends on your perspective. Now, what we're trying to get you to appreciate here is that your beliefs can send you down rabbit holes. Math is the only thing I know that doesn't lie. People do. However, as we go through our engine building process, we need to do autopsies to evaluate, learn, go to the next level. But we've arrived at a point where fundamentals, law of physics are still in play. So me telling you guys to stop making so much horsepower, your reply to all that is, hold my beer. And so you'll go ahead and you'll send us right over the cliff. Again, a form of entertainment, if you will, but just an expensive process. So when we talk about engines of today, they're still rooted in the fundamentals. Pistons go up and down, cranks go round and round. But you have to understand all those components now have to be synchronous. Literally a symphony, if you will, of an agreement to work. Any one of those components can cause amazing problems or amazing power. That's where you guys, that's your technique, that's your skill sets, and learning that is important. So we're going to focus a little bit on load. For instance, on every engine that runs, you're going to see this event, and it's caused by torque. Well, torque is horsepower, right? So the point is, the mechanical side of it is you're going to see deflection. Now, over time, and I'll use the old adage, if I take a beer can, after I've emptied it, by the way, and I start twisting, I'll get two for the price of one. It will shear and break. Again, not a goal. So I want to start at this end of evolution of cranks. Back in the day when we used to put old Roots blowers on, we really found out very quick that the post really couldn't handle that, and so we put a secondary key into it, and that worked pretty much as long as you didn't have a lot of drag. Well, when we get into top fuel and so forth, now you notice this right here, you see the multiple spline, not only is in the blower drive, but it's also in the cam itself. The deal is we're dispersing load over the post end of the crank. Well, it works. We've evolved to that status. But let's go back to something more like normally aspirated motors. Now, this is the actual picture here of an RY45 system. You'll notice that the holes on the very end there, we moved the damper back. We moved it closer to the main. And the real reason, any of you guys that have been in business long enough, you've seen engines, and I don't even use the LS, it's got a rather long post on a crank. So you have this damper, you have all this device hanging out there, and literally it whips in the wing. Now what happens is that kind of load transfers right through the rest of the crank. So we have a flexing unit. That's not the goal. So what we want to do is understand this is really how everything's going to go forward, and we're going to use this example. So you can see we moved the damper closer to the number one main. We in turn have had to extend the cam out where we now add another bearing, which by the way, really pretty cool, so it keeps that little bobble at the end. Now the belt drives, gear drives, whatever you're going to do there, that's another subject at the moment. We just want you to understand the primary interest we're showing here is move that damper or that mass closer to support. Now a good way for you to visualize that, all of us at some point in time have been out on a pool on a diving board, and as you walk out on the end, you can see the spring action. So if we have anything that generates energy and is hanging out in the breeze, it's still attached to the rest of the crank. So that kind of influence is all negative. Now, this is Dan Begle, who originally passed the genius, by the way. He had come up with this and was very similar, if you will, to the general design of the RY45. This is the right path right now. Now, fortunately, Jason Lyons picked up the ball and he's running with that. And if you see, I know Jason's at the show. If you get to talk to him, there's some pretty interesting features in that design. Well, here's a poor boy approach. And basically what we got is the Mullen post. And what we're simply doing is just shorten them up. Now remember, your OEMs, they have to run power steering, air conditioning, all this other stuff, and that's their intent. And we, as an industry, want to take that profile, or that platform, if you will, and turn it into a race application. You're going down a rabbit hole. You're going to sit there and create so much chaos on the front half of that motor that it affects everything connected. Now, I want to go in a little bit more. A lot of you guys have put heavy metal in cranks. I want to just show you a trend line of where we're going. One of the biggest concerns, we don't have enough real estate, especially with this big cubic inch application, to get enough weight in there. And in doing so, some of the guys are running these things, they're filling as far as they can, and they're running what we call under percent balancing. In other words, instead of 50% being conventional, you're seeing guys go down to 47. I even had one guy go down to 45. And I asked him what happened at 45. He says, it wasn't good. And so what it simply means is you went too far in the wrong direction. Now, with that being said, it's also driven by the application. Drag racing has its path. Le Mans would have a different path. Dirt, 410 group. That's why, by the way, I have a couple of great guys up here. We're going to bring John up shortly and Tim. And these guys have, well, what I consider worldly experience. And they're going to go ahead and help answer on the Q&A side. So be advised that's headed your way. But I'm going to show you a different path. Different path is we're going to actually notch the crank and we're going to turn it into a tungsten insert. And so, in fact, this, by the way, Callie's has been instrumental in this discussion. So I'm going to give you a little bit more heads up, and this is how we're going to fasten it. Once again, that's why I have Kevin here. Kevin is the fastener guy, and we have a lot to talk about on fasteners. But this is not new. That's been around for a better part of 30 years. That's just a finished example. That's an aero crank out of Europe. Now, when we get into this, and I want to lead into this very quickly, we have a situation where we have an FEA, and what we're showing is happening only on the front, and this is all exaggerated now, so don't get carried away. But the point is, you're watching this thing gyrate. So we're seeing a lot of deflection, and you're seeing it in witness marks on the bearings. This is where Dan's going to step in and really clean up my act here. So as we go, though, I just took a snapshot, and I'm showing you a peak of deflection. Notice the post angle, and notice the number 2 main. Now what we have is this rocking motion. In fact, we're seeing and just notice I highlighted in the red, and we're going to see something that you never really understood before, and that is the counterweights are becoming unstable. So when we talk about RPM, we look at that in hertz, all right? The problem with the flutter that's generated by this, and by the way, when you drill, everyone's seen these cranks that are Swiss cheese at best. They are already totally violated the integrity of that counterweight. So unlike some of the known frequencies that we now have a new, what we consider a contaminant frequency that's very erratic, and it changes radically with RPM and load. Now, I'm going to turn this over to Dan because, quite frankly, this is pretty cool stuff.
Thanks, Randy. So before we start talking about bearings, I always like to say, what is the fundamentals? How does a bearing work? You know, simply saying it's as you can see in the picture there, you got the shaft, you have a bearing, the brown representing the oil. So as we speak about bearing, this is what we would think is the load. All right, load's coming down, shaft is spinning, and at that point, the bearing has eccentricity. The eccentricity creates a film pressure. So I like to think the easy way to describe it is if you have a door stop underneath a door, a wedge, if you kick the door stop underneath there, what is it doing? It's keeping the door from closing. How does that work? Well, it's putting pressure and lifting the door up, causing resistance. All right, so you may have a engine, it has 100 pounds of oil pressure. This bearing in the eccentricity with that wedge going in there is taking a small amount of oil and trying to squeeze it. We have bearings that are capable of holding in the excess of 30,000 PSI. So it's not uncommon on just a standard automobile application, aluminum bearings at that we're developing 15,000 pounds of film pressure to keep the shaft away from the bearing. Okay, and so in saying that, so typically speaking, this is actually what happens. When the engine's firing, the left is a FEA graph, that's what is happening with the crankshaft. The right is just an animation to represent that. But that crankshaft main, in this case it's a main, is bouncing around all over the place. Now, every time you could see it's filling up. Now this is a case in the FEA where we had deflection in the crankshaft. All right, so what happens is, as we were showing the FEA, the crankshaft bends. As it bends, it's what we call orbiting. So as you can see how close the animation autograph, whichever you choose, gets to the outer side, it doesn't have a chance to put much oil to create that film pressure. It's actually beating it out. So you're exceeding the pressure of what's happening, what that bearing's capable of, and by the crank orbiting. So you wonder why you have contact. You may have contact in unusual places because of where your minimum oil film thickness is at, because the crank is flexing around from some harmonics going on. So again, typically speaking, in this case, you have an FEA and of a main bearing number 4. And another way, this is accurate information that Molly did for a manufacturer. So this is testing that we have did, and the FEAs to do that. You know, in this case, this isn't bad because it's always maintaining film pressure, and it just bounces back and forth. So this is not a high horsepower engine, but this is what really happens. So now you have a situation, exaggerated, you're added power to that engine of what we just had. So you can see all of a sudden you have a minimum contact or a minimum film, and you get the shaft, which is actually contacting, creating frictional heat in the bearing. Frictional heat will then eventually start to melt the materials in the bearing. So a typical bearing in the world is a copper tin lead. So the bearing is only as good as the frictional temperature that's created that melts the components of copper, tin, or lead. In this case, you have your tin and lead. By 620 degrees, you have melted out the tin and lead. Okay, so and once you start melting out, and you can always tell it when you look at a bearing and it comes apart, and you can start seeing black streaks in it. The black streaks is the tin and lead melting out, overheating, and coming out. So basically, you get a small contact, what it's doing, and it keeps repeating. Your harmonics keeps repeating in that spot, and it keeps putting frictional heat, frictional heat, frictional heat, till finally it says, ouch, I'm done. And then it bearing spins, failure mode.
Let me step in for a second. One of the things that these illustrations do, they give you a visual perspective, but understand this is a picture of one main. When that engine's running, all 5 are now not doing the same thing. They're independent in that function. Because remember, you're changing power front to back, side to side. And so we have a lot of applications where we're seeing some flex through the crank, and it's because of this multitude of disbursement of load. Well, here's an example. Dan and I got in this project a couple years back, and so we were called in and said, hey, what do you guys think of this? So Dan, pick up.
So this is a number 2 and a number 4 bearing from an LS, high-end, high-power LS. So as you can tell, if you look at, these are uppers, all right? So you typically think, all right, we're going to have a bearing failure. It's going to be a lower because a main bearing, again, because of pressure firing in there. Well, hopefully with the FEAs and the animation, you can see that's not always the case. So these were perfectly cool bearings, not in a good way, but great illustrations where you can see the uppers are having wear. Now, if you notice, half the bearing is untouched. The other half has wear. And this one I thought was really interesting. Can you see the arc? That's how radical that crankshaft is flexing, that it's not even contacting all the ways across. It's actually arcing across. So it's a quick bounce, and repeatedly. Now, as I shown before, this keeps up, you start melting. These are coated bearings, so the coating is gone. Once the coating's gone, the overlay is exposed. If you don't have coated bearings, you're already at the overlay. You start melting out the tin or the lead, or if it's a lead indium bearing, indium's even melts earlier than that. So at that point, the overlay starts to melt out, creating the failure mode.
So let me follow up with that also. Now, keep in mind, when we first looked at this thing, my first go-to was a geometry problem, alignment, roundness, whatever you want to call it. I look at what we call cylindricity, straight and round. Well, the engine builder that we talked to is well-known, well, just a really sharp guy. And he said, well, it could be. He said, so I'll check it. So he went back, he did everything in the world. And this is not a guy who does this as a hobby. This is a high-end guy. And he called back and says, sorry, guys, this thing, it can't get any better. So we had to play around a little bit. And this thing is now starting to permeate. We're seeing more of this. It's an unusual configuration. So we look at cause and effect. And so we found out that it was the crank design was the problem. But it also had a working relationship to the amount of power made and the RPM of cycle. In other words, when we talked about this orbiting effect that we saw in the clearance, a lot of you guys will do things, you'll see some swiping on the edge, say, well, what we're going to do here is we're going to open the clearance. Well, the problem with that is, Abe Lincoln made a statement a long time ago, all men and all rivers seek the avenue of least resistance. Well, oil will never run to load. If it has an escape path, it's going to do it. Now, what happens that we found out was that the crank design was rather interesting, and we have been proponents of 8 counterweight designs. But we found out that it is a design specific to application. In other words, if I got 5,000 RPM and I'm making 500 horsepower, I can do a lot of stupid things and it'll work. All right? Or as I start ramping that up in power making, meaning more power, or I start changing, in this case, the RPM, this is when there's a sort of a curve that takes place. It's just north of about 6,000. Not every engine, so keep in mind when I say this, every engine has its own personality. So we have to understand even the counterweight designs are specific to application. Now, we have a 410 expert here, all right? These guys don't like anything that's heavy. They don't want 8 counterweights, end of story, and we understand their mission statement. We'll talk about that in a minute. But what I'm trying to get to is, this is pretty much an ultralight type unit, and what we have is a 6 counterweight event. Now, you notice the phasing of those units basically are set up to help comp the fact that there's no center counterweight. Now, this was started back in 1950s, 53 to be exact, but it was done because of economy, the ability to make something cheap that would function within the scope of application. Well, what was that? Well, 3,000 RPM was the standard. 4,000 at best, and my God, it'll blow up at 5. Well, you know, listen, we're not in that era anymore. So what we have now is 8 counterweight applications. What's interesting about this is when a designer makes a unit and they have to send it overseas to have it actually turn into a finished product, there's about a year lag time from the time he launches the order to the time it gets back here and goes into service. And in doing so, what we have found is misapplication of the center counterweights and to include the other counterweights. In other words, you call it phasing, I call it clocking. So you have to understand this is a new era. You cannot look at the power making that you're thinking about in the future and be catalog part number, blah, 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 let's run it. You're going to have to do a deeper dive and understand application. Now, it's on you. Because the guy who made that crank that's in it a year back, he really doesn't want it to stay on the shelf. He would like to see you own it. And then he'll talk about it later. Well, listen, we understand it, we're seeing it. It's a trend line that is really unusual for us to see. So be aware, your future going forward, application is, in other words, engines are systems. And so as you change power making or application in general, the system still has to be implemented.
Randy.
Yes.
Yeah. Well, I add one thing to that, what Randy said. Recently, I was working with a customer. He was building a 632, 1,200 horsepower engine, and he was having problems with some main bearings. So I got involved in it, and he built a lower horsepower engine. They put the same 6 counterweight crank in there, made 6 dyno pulls, killed the mains. Like, the wrong crank. You can't run this low horsepower crank 6 counterweights, to Randy's point. So he went and bought an 8 counterweight crank. Don't know where it came from other than it came across the ocean. And put in there, and he picked up from 6 dyno pulls to 11 dyno pulls before it killed the main bearings. And he goes, something's wrong here. And I was like, yeah, there's definitely something wrong here. So I said, send me a picture of the crank. So me and Randy talked about it. We were looking at it. And also we identified that the counterweights on the 8 were the exact same as the 6 with the addition of just 2 more in the center. And then what it was doing is, as it was rotating, you could spin it, balance it, because they have Randy's machine, and they balanced it, everything was great. The harmonics going in, because of the counterweights being wrong, was totally throwing the thing in hysteria as it was running. So I stopped the test. I said, I recommend that they stop the test. They listened, and they were waiting on a Kelly's crank. And I said, just wait your tests, don't do any more. And so they got the Kelly's crank in there, put in there. The next time they made pulls, they were at 90 pulls. They had another issue. They had to shut the engine down. 90 pulls, they pulled it apart. Bearings looked great. And it was all because 6 counterweights failed. Wrong 8 counterweights failed. But put the right counterweights with a properly designed crankshaft, it worked perfect.
Keep in mind that application at lower horsepower, you'd have never seen it. All right? And so what I'm trying to get you guys to appreciate is you're power makers. You're the ones that, you're not going to settle for what you did yesterday. You're going to keep pushing that envelope. What you have to understand is the direct association with the component that you have is going to surrender unless it's properly designed. So yes, it costs more, but I got to tell you, the goal here is not to send a product out that won't live. You want to kill your reputation real quick, make lots of power and blow it up and see how long you last. Won't work well. All right, staying on the crank though, I want to show you a couple of things here. And again, Dan had brought some really cool data in that I got to tell you, you learn every day. And right here, this is important.
So if you get involved in some of the newer engines, also you notice like main bearings look different. And you think, what's the difference between a hole and a slot? You're like, there's a lot of difference. This is true data that Amala did testing to find out. So in this particular OE application, they had a main bearing. And what I'm going to do is show you steps of a main bearing change and the difference with the amount of air trapped between the main and the rod. All right, so in this case, we had a 210-degree groove. There's the measurements of the groove, 9-millimeter hole. And that application, as it came out, was 73% of air. Now, I believe everybody knows air compresses, and it doesn't lubricate. So failure mode is going to be rod bearings because of this design. So we were tasked with making some main bearing change and doing some testing. So our next one, we changed and we put a 180-degree groove. Notice this time, slots. Changing the oil phasing of when it's going to go from the main to the rod, okay? Notice here, by doing that change, we changed the air to 41%. Okay, better. It's going to run a little longer now, but we still have an issue of it creating air. Now you have no film pressure in your rod bearings. Now, imagine if you add horsepower to that, you've just made a failure mode. All right, so next test, we moved on. We did a 160-degree groove, or I'm sorry, a 180 groove, but it's a big, long slot. We had to add all kind of timing for that main bearing to feed the rod. And we knocked it down 17% air. So it's pretty cool. It's pretty scary. All right, so a lot of people are like, we're going to modify these bearings. All right, my word of caution is you may do well, you may screw it up. Because there's a reason, there's a lot of testing done as far as oil phasing. Now, here in the racing world, we change cranks, we do this, that, and it kind of throws it all out the window in a lot of cases. The OE guys always laugh at me and said, man, you live in the wild, wild west. You just kind of like try stuff and yep, that's the way we roll. But the reality is sometimes you're chasing a problem and you're not looking at the right area. That's my point of showing a main bearing, and you're looking at rod bearing failure or something like that. Rod bearings not look good, and you're like, what's wrong with my rod bearings? What's wrong with my rod bearings? It's not. It may not be the rod bearing at all. It may be nothing to do with that. It may be the feed of the oil from the main bearing.
Let me add a little bit more to that. Take notice of that bearing. Look at the actual, what we call the bearing contact area, as opposed to a full sleeve unit with a little single hole orifice. The guy says, well, wait a minute, hold on. That load has to go somewhere, so we need to have support. Well, you're going to find in a minute I'm going to be bringing something up that's sort of going to change your thought process. And by the way, I'm holding Kevin here in reserve because he's about to launch a lot of good data, and he's being very patient with me. But at the end of the day, we're going to go ahead and start migrating some of this information, collecting it so that fasteners, bearings, clearance, balance, all of this is integral, and in fact, it has to be developed in a system platform. So, Dan, run with that.
So some of the stuff we looked at is flex, main bearing, cap flex, what's happening. We're adding more power, creates more harmonics. Blocks are getting lighter, need better fasteners. And so the prior slides was to show you how some of this oil affects rod bearings. Now, in this animation, you can see, so as you added power and you have, whether it be cap flex, you have bolts that are fasteners that are not holding. So as you have distortion in that, what happens? Watch what happens here. You get load come down here, the flexes, what happens to your oil clearance up here? What you set in the shop is no longer relative because you turned the engine on. Plain and simple. Now the cap, there's movement, you've increased. Remember I said earlier, you may have an engine that's building 25, 30,000 PSI of film pressure in that between the shaft and bearing. You open that clearance up, how do you get pressure? Pressure is the resistance of flow, right? So if you open that clearance up, you've increased the flow and decreased the pressure. So remember I just talked about getting air induced into the main to the rods. You just did it right here by cap flex in the main, decreasing film pressure. Now you have not enough film pressure to go between the main to feed the rod, and you're starving the rod of oil because of cap flex.
So before we move on, I want to remind you the importance of understanding you're seeing one main activity. Correct. As we increase the amount of clearance, this is exacerbated even farther. And in fact, it turns into almost a slide hammer. So it attacks the first order of balance because we're not rotating anymore, we're orbiting. And as in some of the previous illustrations we put up there, you can see how it's going to attach to the bearing, meaning contact. You're going to get a friction component or a relationship, and you're going to see a failure because you actually made more clearance. And the vibrations generated is, and as far as we're concerned, once you vibrate any part of that engine, the whole engine is a sister to all that action. It's very important you understand that. Now, Kevin, one of the things that your company has done, and this, boy, if you guys ever have the opportunity to go out of Missouri, if you want to see a first-class manufacturing, over-the-top company, go see them. I mean, Dan and I have been out there a couple times, and every time we talk for 30 minutes, every time we leave, say, I didn't know that. I didn't realize they could do that. It is first cabin stuff. So, Kevin, tell us about this block.
Well, Randy, I appreciate the opportunity here. So the presentation we just looked at with a lot of the examples of the, crank flex and what's taking place, until that last slide, it was all, it wasn't dynamic, right? It was assuming that housing bore is staying round and stable, throughout the cycle. That last slide shows us what actually happens, in application when it's dynamic. This slide here is our top fuel block. This is kind of a luxury that we have because we manufacture the block and the fasteners. It's the only application where we can control both sides of the equation. Randy talks about how an engine is a system and how everything needs to work together. Well, fasteners are a system. I mean, you've got the male portion of it and you got the female portion of it. And most of the time we can't control both sides of that. In this instance, we have the luxury to do that, but going back to Randy's point about, power levels, this design here was introduced in 1964 and it made a whopping 425 horsepower. It's the same basic design today that they're producing, 12,000 horsepower in top fuel class. It's a great example of fastener strategy because you have 4 bolts in this tension joint and then you've got 2 in shear. And everybody thinks that's kind of a tension joint and shear joint. That's pretty straightforward, but getting back to the dynamics of it, I mean, when you get a tire shake in one of these fuel cars, that becomes a combination joint. It's no different than a rod bolt. It's moving in every which direction. So in this block design, we had the luxury of designing the cap, form, fit, and function of how it integrates into the pan rail, when we torque it up, it captures the cap into the main bulkhead of the block, all at the same time. So we can control every aspect of it. But really what I want to focus on today is talking about just good practices. There's a lot of misinformation. Just recently, Dan and I saw a lot of stuff floating around out on some of the forums here, and we want to share fastener strategy. We could talk for hours about fasteners in themselves, but we just want to talk about proper installation and lubrication. So we're going to start with some of the basics.
So here we go. When we go into this, one thing that we all know about torque wrenches, right? So we think that's the guideline for everything. Not so much, all right? We've heard about bolt stretch, we've heard about all these things, but a lot of people, and this is what Kevin's going to be showing you here, these are fundamentals that are always overlooked. And I got to tell you, it is scary. And like I say, when Dan and I were out there and we first had the run through, these guys sort of presented this stuff, and I said, oops, I've done that, and I've done it wrong. And I'm going to show you, and Kevin specifically is going to go right in that, because this is the heads up deal here, guys.
So going back to the fastener, it's the most underrated component in an engine. I was a consumer of it for years as a manufacturer, really didn't understand what a fastener did other than holding a joint together. So we always talk about torque, and people think about torque as, tension, and you're creating tension with torque. Well, you're not really doing that. Yes, there is a relationship to it, but torque is just the means of creating the clamp force in the fastener. And it's simple math. And as Randy says, numbers don't lie. Torque equals your friction factor, the diameter of the fastener, and tension, which is your clamp load. And it looks like it's simple math, but everything's simple until you get to that K factor, which is the friction. And the easiest way to kind of explain this is if you take a rubber band and you wrap it around your fingers, and you just think about when you're putting that in tension, which is created with torque, you're stretching that rubber band out, and that is preload. That's what you're loading the fastener with. And then the opposing force is clamp load. I mean, a fastener is nothing more than a spring. I mean, it's Hooke's law. It's just the law of elasticity of how much you can stretch that fastener before it has permanent deformation, and it creates a resulting clamp load. And then what we really need to focus on the application side of it is really what the service load is. You want to make sure you have enough clamp load that in normal circumstances that the service load doesn't overcome what your clamp load is. And that's when you start seeing some of that, cap moving in a block. So the K factor, this is something that blew me away. I mean, and you can research it on the internet. Only about 10% of the torque input that you put into a fastener actually is converted to stretching the fastener or creating clamp load. It's debatable if it's 35% consumed in the threads, 40%, 55% under the head, 60%, but the fact remains it's about 10% of input only goes into creating clamp load. And that's just pretty amazing. And the friction factor is the only thing that we can control. I mean, torque is torque. The diameter of the bolt, the material, all that is just simple math. The K factor isn't so simple. I mean, people think it's simple. You can look up charts, and the charts will say, given this, this particular lubricant, this is a K factor. But there's a lot more to it, the components of the lube that is being used, and the proper application of it. So proper lubrication when you're on a fastener is you want to make sure you judiciously put it on the fastener, on the threads, and on the underside of the nut. You do not want to do both sides of the washer, because that washer, if you lube both sides and it starts turning, it creates like a Torrington bearing, and then in result, you lose your consistency and your friction factor.
How many of us out there have ever done what you're showing here? Yeah, come on, you cowards, put all your hands up. All right, that's one of the biggest eye openers. In other words, we have false input. Remember I started at the beginning of this thing, our beliefs dictate our policy. Well, we're trying to put the math back into this thing. We're trying to get you to understand, whoa, 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 whoa. I may want it, I may wish it, I may promise it, but until you get it right, you're not gonna get the right result.
So what I want to kind of show here is, again, there's been a lot of talk on the internet talking about different lubrications. We've got a torque point lube that we recommend. We provide it with all of our fasteners, and we provide all the data for torque input and clamp load utilizing our lubrication. But there's guys out there that say, well, I just use 30 weight oil, 5W30, or Detroit number 2, which is peanut butter, and I use that on everything. And can you do it? Absolutely. I mean, you can use whatever you want, but the results is what we're looking for. We go back to the looking at the clamp load for a particular joint, and we want consistency. It's a 4-bolt main we are looking at. We want to make sure we have as tight of clamp load on each fastener across that joint and not having, a big spread. So that's where it's really important to have the control the friction in that system. Key factors for this, choosing a lube, is we're trying to avoid galling. Okay, you got galling in the threads, you have galling underneath the head, between the head and the washer. Not every lube is good for every fastener. I mean, we have certainly tried to find something that would be one size fits all, but the higher loads you get, it really has an effect on the lube. And everybody does it in their shop and they say, I torque it up, they feel great, but do they know what it's doing? I mean, and the answer is, unless you have some sophisticated equipment like we do, you don't really know what it's doing. We have a torque tension bench. Every fastener, every batch of fasteners that we produce, we take a sampling out and we do torque tension testing, so we can tell you exactly what that batch of fasteners did, using our lube, using a consistent process. It's got load cells that measures the friction under the head and frictions in the threads. So the rest of it is just guessing.
Guessing's a bad policy, all right? One of the things that we were so impressed with, Dan and I, in fact, Dan still says he's going to take a week and live in that room. If you can't measure it, you don't know. Let's just be clear on that. But none of us, probably for the most part, have this kind of equipment. These guys do, but they are dedicated to passing on a heads up, hey, we do know what's going to happen. We want to give that data to you to build a better product. Once again, we're back to the system. I don't care how much power you make. We got to contain it. Now, it could be in block design, it could be in fasteners, it could be in materials and processes. But this is the way we're going to go future into all of our needs for the future of our shops. If you want to make bad products, knock yourself out. If you want to move forward and build a better product, make more money, that's what's going on here. So I let this out here just for the simple reason, if you can't measure, you don't know. So I wanted to use this example, though, here to really expound on what you're saying. So within the scope, I'm going to put it into a little animation here, so if you can kindly pick that up.
So what we're showing here is the difference between the torque point lube that we recommend and provide with our kits, 5W30 oil, Detroit number 2. All three of these applications have the same torque input. 110 foot-pounds. This is a 1/2-inch fastener that we did, so everything remaining equal. Only difference is the lube. And if you look at the torque input and the resulting clamp load, which will be on the next slide
right
here.
That's coming up now. This is the deal that woke me up right here. Look at the numbers.
So look at the variation of numbers. That is really what the key to this presentation is. Consistency. If you look at the line on the graph on the left, It's very smooth. There's very little scatter in the results. The clamp load is 16,700 pounds. Same fastener, same torque input on 30 weight oil, we're 10,200. Detroit number 2, commonly known as peanut butter, a lot slicker, so it's a lot less friction. We yield it apart. It's gone past its yield point. So it's well in excess of, 16,700 pounds. And you can also look at the rotation. Rotation with torque point is 150 degrees. Rotation with the oil, 108 degrees. Rotation with Detroit number 2, it's 170 degrees. So that's the difference that we're seeing in stretching that fastener. Everybody's used to stretching on a rod bolt. You don't have the luxury of measuring the length of a stud when it's installed, though the equipment's getting a lot less expensive now that you can. But that's where torque angle comes into play and giving you a more consistent reading. But torque is really the most common. So this is the staggering one here. Going back to that joint, we were talking about 4 bolts, wanting to have the same clamp load across that joint so you have consistency in a dynamic application. If you click on it again, Randy. Clamp load variation. This is the key. The last slide, we were showing you what the goal is for our clamp load at 16,700 pounds. Here with our torque point, we're 15,744 to 17,359. So you got a pretty tight range of, less than 1,500 pounds across that joint with 4 bolts. Now look at the oil and then Detroit number 2. You got a range of 8,000 pounds. 8,000 pounds. We're talking a 16,000 pound clamp force that we're looking for, and we can have a variation of up to 8,000 pounds. And you want to talk about that bore, going back to the dynamics of it, right, Dan? What that crankshaft is doing, and when you're, under a dynamic load and you have that big a variation in your clamp load, that bore is just distorting. So really the goal here is the correct lube to effectively convert the torque into a fastener clamp load. Avoid galling, controlling the friction, and really getting repeatability. And that's the thing that I don't think people understand. There's a lot of devices out there that you can measure clamp load, a skid mower, just a load cell, and do some testing. But unless you have the tools, and the luxury to be able to measure exactly what it's doing in application, it's kind of a guessing game. Like I said, we spend a lot of time, a lot of research, and trying to find the best lubricant and having consistent results. Sometimes it's messy, There's lubes that aren't as messy. And, and I go back to when I was a teenager when I learned to line hone blocks the first time. I'm line honing a block. I'm not going to spend all that time putting lube on it, I'm going to hone the block. We'll lube it when we assemble it. Well, little did I know, I created a disconnect in the system because that bore, now that I added the lube, it's not going to be the same.
Right.
So you need to be consistent, very regimented in how you apply it, throughout the process.
Yeah, just adding to it. We're bearing guy. We're talking about mains, but the cylinder heads. The same thing applies to cylinder heads. So you're honing this, the guy honing the block cylinder walls, and you put the torque plate on. You're doing everything what you think is right. Kevin just proved that is not right. If the guy in honing is not doing the same thing that the guy in assembly, and they're both doing it correct.
Yeah.
Okay, so one of the things I want to introduce here, and I'm going to put it up in a little bit, we're going to put our booths out there, and we realize, and again, I'm very thankful you guys are listening, but one of the reasons of coming to the shows is when you go from here, come to our booths. We'll answer this in greater detail. So this is what this is all about.
We don't have slides to ask the question to.
We're coming up with questions shortly. Okay, but I'm sorry, maybe I misheard that question.
We show up at the booth, we don't have the slides to talk to.
Yeah, but I got a crayon. Okay, so I appreciate what you're saying, though. And by the way, remember I said about non-interruptions? Okay, you're not my wife. You don't enjoy that. Okay, hold on. Only playing. All right, so here's one thing. Mark Conquest, he's sort of an interesting guy from Cubs. And the bottom line is, he made a statement that's just gnawed on me since he said it. And he said, when we don't understand what's going on, we call it harmonics. If there's a voodoo area of conversation in engines, harmonics is it. So what I want to do is give you a little bit, we've shown this before, but it's worthy. What we have is an example of two tuning forks. They're being isolated away from each other, and then you'll see a ping pong ball hanging down there. And so what he's going to do is disrupt it by striking it, and you're going to see a response to the associated tuning fork. Now it is connected, but by air only, all right? So frequency intercept is what we're talking about here. So whenever we have components, remember I talked about the systems, we showed you the engine, all these things moving. It only takes one trigger to set off the bomb. And so the problem is if you stay in that frequency, it'll continue to stay excited. So I'm going to give you another example here. And this is something that's sort of basic, but watch what happens. We talk about fasteners. This is what we're, so we put the proper materials on it, we torque it, we do this. But now look what's happening here by the excitation through harmonics. Notice that bolt is climbing vertically. And what we're saying is even though the fastener is, well, let's say properly clamped, right, has proper torque. If I intercept that with a known frequency of excitation, you're going to see what just happened. This is the voodoo side from your perspective, but it's really a science. Anybody that's played a musical instrument, or my voice, in fact, is different than everybody else's. The tone, and once you hit natural frequency, John and I were talking the other day how in the old days we were doing these burnouts, and we would kill the valve spring in the burnout. And so as they would stay at that frequency at RPM and do these long John Force type burnouts. Well, at the end of the day, the spring just says, it went cherry red, was annealed and collapsed. They hit the critical frequency. Now, here's the interesting part about frequency. You don't know what it is. You're going to have to find it. And it's a case-by-case deal. Components. Sometimes you have to change just the thickness of a push rod. Sometimes it's a material change. And in this case, fasteners clamp pressure. In other words, Hooke's law does govern that if I can contain it, it can't vibrate. However, if I hit natural frequency and give it time, that's the key point here, time, it will do what you consider friction welding. You'll see it on the post of the crank, you'll see it in mating caps, you'll see it on the deck surface, you'll see it on the timing cover, front and back bell housing. You'll see fretting, and the only way that can happen is through a frequency excitation that you've seen components heated up and with a frequency coil, and they go cherry red in a matter of minutes or seconds in some cases. The point is, if you arrive there, there's only one remedy. Get the hell out of there. You cannot. If you're like a drag race where we're just passing through those frequencies, no worries. But if you're a Le Mans type guy or road race type application and you're a constant throttle and you hit that frequency, you're not going to have a good day. So let me just speak real quick that basically we look as a frequency as an event happening over time. And I don't want to wear you guys out on this, but I want you to simply understand we know how to measure it. This is things that you have to be aware of, and you have to start looking at individual components and are they synchronous and working in symphony or harmony, however you want to put it, in a relaxed state. If they do have a critical frequency intercept, you have to figure a way to get around it. So when I look at basically an FFT, you're going to see a series of graphs, and I know this is a little confusing. What's important is you notice all the way at one given point, it came to a peak, which happened to be right about 5,500 RPM. But believe it or not, that one line right about that purple one, that's going out to 330 hertz. These other ones were sitting anywhere from, well, let's just say 40 to 60 hertz. But once we intercept, things go bad, and they go bad quick. Now, here's the generator of a lot of that, torsion. Torsion, I used earlier beer can effect. Well, you do this long enough, and this is what your radius is going to look like on your crank. In other words, you stay there too long, and you exceeded so much pressure that torsion and time have basically yielded the part. In other words, it's just not happening anymore. It's going to, well, keep going, you get two for the price of one, all right? Now, let's go back in the other direction, because now I'm going to kick back to Dan here for a second, because as we have, and I'll use top fuel, funny cars, there used to be, Tim, you would be the one, 3 to 5 runs for a crank, call it a day. Well, we're a little better than that now. In fact, and I can't give exact numbers, but I'm going to say we're doing double digit. We're now running, and so we made a couple changes. The processes are process and materials. So in doing so, we've increased the radius to give it more structure, more flexibility, if you will. But Dan, what happened to your bearings?
Yeah, and I'm all for bigger radiuses, but the problem is you can see what we have is as the radius increase, the picture on the left there, you can see the bigger radius gets into the flat. If you don't address it with the bearing, you get point loading on there. So if you notice on most of the manufacturers, they have a narrowed version or a modified version, and if not for that application, something you really need to look at, because there's several applications that we get. This is the drawing from the crank manufacturer to where I'm creating a bearing and changing the width of the bearing to fit in that radius. So you get the more radius. Not a crank guy, Brooke. I saw Brooke back here. He can answer any crank question you have. But you're building more radius in it to solid. It's just all the FEAs. You have flex. You have flex from the rod pin to the main. So by adding a bigger radius is basically adding a more material, gusseting to take that flex out. So win, but make sure that the bearing fits that radius.
One of the things that is also interesting, and I got to tell you, we're still studying this and trying to figure out, let's say, well, if 3/16 rate's good, how about half inch? And then all of a sudden, you're compromising the actual load area for the bearing. I don't know that we have a good number on that.
I don't think so.
No. So it's, I'm back to you guys, hold my beer. You guys will do things, and then we'll sit there and say, that can't work. And you say, what's this? And then it makes us go down, do a little bit more investigation. However, I will ask you to go back and apply a little logic. Don't go from 3/16 to a half inch and then give me a call. All right, we're going to sort of wind this thing down because I want to bring on 2 other guests up here shortly. But in dynamic balancing, this is a part linkage, is the exciter, or the biggest exciter we have in the engine. If you don't balance it and you don't put it in what we call couple. Now couple, if you'll look at that, that's just a snapshot of one of the screens. But you'll notice the TDC and BDC, they're 180 apart. And what that does is it creates an issue that actually in the center, now I'm just using a 2D effect here, but you'll notice that the principal center line of axis, and then you'll see the CG moment, that's really neutral. Now, I'm not talking about a combustible load. I'm talking about an excitable tool. And what I mean by that is if you take an object and you hit it, it'll probably resonate. Well, if I sit there and and I'll just give you a quick illustration of that, I go ahead and I don't have cancellation. Every rotation, I'm going to get another pulse that's not being canceled. So as we go to the higher levels of building engines, we want to find a way to, I'd love to say sequester it, to totally wipe it out, but the fact of the matter is you are building a parasitic event. And as the balancing shops are out there, they need to start paying attention to this. The higher horsepower, the higher loads. I want to just go back one more and see this deflection side. Take notice of the counterweight. Now, the reason I want to touch on that lightly, all of us typically drill counterweights. Easiest, fastest way to remove material. Or the other ones, we add material. Well, in this particular case, you know the FAA is showing the counterweight in red, and if you look on the bar graph on the side, that's not a good place to be. So as we drill, we cannot make that stronger. As we increase load, horsepower, if you will, then we're going to see deflection. But believe it or not, it's not singular to load by compression, but actually in an overlap cycle. So what happens, just think of these things squeezing in and out, in and out, in and out. John's going to speak to that a little bit, and I hope you guys ask him a question on that because he's got some pretty cool feedback there. So we do have operation control with, instead of drill, we now have software and machinery that can cut the units on lathe, thereby keeping the counterweight structure in its best optimum position. You cannot drill a hole in a counterweight and make it stronger. It won't work. Now, people confuse that and say, well, what about gun drilling? Different subject, totally different subject. I'm talking about counterweight only. The counterweight has 2 functions. one, counterbalance the amount of load generated by the mass being moved, but it also is a damper. And if it is unstable, it becomes an exciter, which is something that, interesting enough, is not frequency-based singularly. In other words, it goes in, I'll use this term, it's a little, probably not the perfect one, but it flutters, starts doing this. And it doesn't do it consistently. And it changes in and out of frequency. So the key, you're building more power, crank's got to be stronger, got to be more stable. Now, once again, when we finish up here, I really hope that you guys will take the opportunity to come to the booth. We have other technicians in the booth, but these are the two lead guys. I think you'll find there's a wealth of information, and they are very open to sharing. And that's what this industry is all about. We used to keep these trade secrets. Oh, Bob Glidden crashed the car, has it covered up with a sheet and all that kind of nonsense. Well, we need to be a little bit more open about it. And you're going to find that everybody benefits. So once again, I want to sort of, in this case, I'd love to bring up Tim Wilson and John Kazi, if you guys don't mind stepping up here for a second. We even got you 2 chairs. What we're hoping for here is that these 2 gentlemen specifically, this is real-time racing, guys. These both have an incredible amount of history and multiple changes. And I know Tim specifically, I think he's raced anything that makes noise. And of course, John, I've been fortunate enough to know John for 40 years. Actually, I only live 6 miles from me, so he has to drive by my place every day to go to work. But bottom line is, what I'm hoping you guys will, let's start with this. I'll let you question. I have a few that have already been told to ask, but if you'll start, anybody got a question? I knew it was going to be you. I knew it.
Well, maybe, and this is to you, really. When you talked early in the presentation about a 45% balance and a 50% balance, what does that mean?
Basically, you're taking the reciprocating mass and you're modifying its mass value. In other words, we call it overbalance, underbalance. Cup guys a number of years ago came up with 2% over, and I think that's pretty common. And so I always ask that question, where'd that come from? Well, I'm actually going to go back. Earl Wade, remember that guy? Oh, yeah. Okay. Earl was one of those guys, Don Nicholson crew chief, if you will. And he came up, and I remember in the conversation, he says, you know, you got to look at the type of rings we're running. And there's a high friction component. Now, all of us have seen the pictures of the fish scale, draw the piston through, right? And he says, look at this. Look at the friction there. We need, because of rotating mass, we need to overbalance to help compensate that, in other words, with velocity. And I sat there and I listened to it and I thought about it and I said, man, you're a smart guy. And I really sort of signed on to it for a while until I realized that the piston went one direction, it's got to go back the other. That's called cancellation. So the Cup guys came back and they said, you know, we're hitting frequencies because we're pretty much fixed RPM applications, right? Fair enough? Okay. Now, once again, I want to reiterate, I've got top fuel funny car. I got big motor mountain, right? God, I'm sorry here. Dirt track would be the best way, but 410 group is really 360 group. And then I got my NASCAR ace here, all right? So we have a wealth of data up here on and capabilities, so I'm really hoping you guys will resource with the questions. But to finish your question here is, I'm a 50%er. In other words, I want to stay with that cancellation, equalization. I'm not saying that you can't do things, but I'm also saying I think you're entertaining yourself.
So for any engine application that we would come to you to balance the crank, you would say, hey, you want 50%?
That would be my position, yes. All right, but I'm not your mama. So if you come up and tell me that you want 52, I'm going to document it in a report. I'm going to send it out. But I will tell you this, and I'll be fair about this. Overbalance does not seem to be as critical as underbalance. Okay, when we go under, in fact, Rare Morrison, which is one of the first guys with the big motors, the first thing they came out, and I was talking to Darren Morgan, and he told me, he said, we're running 47%. I says, wow, how'd you get there? Well, we just know it works. See, that's not good enough for me. So he and I have done seminars over the years together, so I went down there and he let me in the door, so to speak. I said, show me this crank. I want to see it. And I looked at it. They didn't have enough real estate to put any more weight in it. I said, that's why you're 47%. And he said, well, yeah, okay. All right, now, here's the bottom line. I said, what happens when you're lower than that? He says, bad things happen. I said, so you went to the wrong side of equalization. Remember, balance in a simple word is a single statement. It's called equilibrium. If you violate that, there's a penalty. All right? So stability is what balancing really does. Durability is the other linkage to it. So does that answer your question?
Well, okay, if you get a stock LS crankshaft from General Motors and you put it on your balance machine, is it overbalanced or underbalanced?
No, it's straight up 50.
Straight up 50?
Yeah.
Okay.
Yeah.
So the OEs would give you a crankshaft, would Dallas give you a 50% balanced crankshaft also?
I mean, an aftermarket supplier? They're your discretion, and they do it typically by the customer's call out. In other words, belief sometimes dictates policy. I'm not in that camp. I'm a numbers guy, right? But I also understand the importance of the customer's right.
So that's for the common pin 90-degree crankshaft. And when you got 60 degrees and
Okay, good point.
split pins and everything else,
Yep, no, great
it's
point.
a lot different.
Well, let's, I don't want to get off this, but I'm going to simply say that the V6, only General Motors, Ford, and Chrysler screwed that up. Right? In other words, Nissan, European guys, 50%. Now, in some cases, common throw, we will sit there and we'll have a counterbalance because they generated a false moment. And the only way to get rid of a false moment, just like second order on a 4-cylinder or even 6-cylinders, you have to have a counterbalance shaft. You guys won't tolerate a counterbalance shaft. You kidding me? You're going to have another, obviously, a parasitic loss? No, you'll throw that out right away. But you're also sitting there and says, I don't care if my butt feels funny when I race. You know, the grandma does. So grandma's car has to have that perfect cushion. But again, General Motors, Ford, Chrysler, I'll just simply say the engineers there had a sense of humor.
Vertical balance versus horizontal balance and split pin crankshaft and
Well, pancake type motors, Porsche, Volkswagen, let's go back to that, Saab, those are cancellation. They actually are very close to neutralizing second order. They're probably 98% efficient, but only because of the stroke difference when they have enough acceleration, deceleration, does it still aggravate? But on an inline system, that's all it is. Second order, well, voodoo cranks, real quick. You notice Ford dropped that bad boy. And the reason it was a stroke over bore configuration. So what happened is the velocity actually set up the harmonic in there. And if you looked at the alternator mounts, they're twice the size and they broke, right? And then if you let them run long enough, the oil filter will fall off or the full pump will fall off. And I joke about it, said drive it enough and the dash will fall out. That is second order dynamics, and you can't, it's a mechanical influence. Unless you have cancellation mechanisms, counterbalance shafts, you cannot eradicate it.
what I'm talking about is like the OEMs recommend, like in some crankshafts, they recommend 44%. Some crankshafts.
Yeah, remember those screw walls I just talked about? They're the ones that told that story. Why is it that the same engine that's called Nissan doesn't have that? Well, I do. Okay. All right. John, can you add any of that?
Well, on the,
Huh? Counterweight set,
yeah,
yeah.
on the counterweight thing, you know, we see on the big engines, because the rod bearings and the main bearings are pretty far apart, there's no overlap of the journals, so the crank is a lot more flexible. And the counterweights are wandering around back and forth like this when it's revved up real high, because the higher it revs, the more it thinks the rods and pistons weigh. So, you know, when the rods and pistons are changing direction at top dead center at like 8,600 RPM and whatever bob weight they are, it's pulling as hard as it can pull on that connecting rod journal. It's pulling it, let's say it's pulling it up, and the counterweights are down here. They say, well, that distance has got to come from somewhere. Okay, let's do this. You know, so they're flexing around, and on some of those bigger engines, you can have 1/8 of an inch clearance between the counterweight and the block, and at times you'll see where it scrubs it. You know, and then the crank will actually get shorter as it revs up. The Chevys are worse because their thrust is at the back, and so since the thrust is at the back, the whole crank goes back toward the rear. So if you've ever noticed, if you've got a big Chevy or something and it over revs and the crank trigger wheel hits the magnet, it almost never hits it in the middle. It always hits, there'll be a big streak toward the front of that, where your wheel is, where the magnets are, because the crank, when it's revved way up, it's back about maybe 50 thousandths, and you know, the little pulley on the bottom hits against the seal and all that stuff, and you wonder why. Well, it's a crank. When it revs up, it shortens up. The Fords are a little different and a little easier because the thrust is in the center, so the back goes forward and the front goes back. But it still shortens up totally about the same amount. But it's total chaos in there, you know, and we try and position stuff. We have a map that we know that works, where we get the rods, and the rods might not be in the center, and everything might not be perfect when you put it together, but when we know when it revs up, the rod will be in the middle of the piston.
Isn't that where piston guided rod came from, realistically?
Well, sort of. But I mean, yeah, with the piston guided, then you have all kinds of side clearance, and that'll account for it. But in our case, we don't want to do that because we've only got so much connecting rod in there, and that thing's dying to break. You know, so we don't want to take material off it to, you know, to have a lot of side clearance. So you try and get it where the side clearance, you know, if it's piston guided at the top, you'd rather that it had side clearance at the bottom almost normal, so that when it's revved up, everything's kind of held in place. But it's a hard map to come up with. Yeah, because the crank shortens up, and where do you want it to be right? Well, you want it to be right when it's revved up and making power, not when it's slow speed. And then the balance on those things, we really can't tell. You know, we almost never overbalance because there's not enough room for it, it costs too much. But if they're underbalanced, we've had some that were underbalanced by 200 grams, and when we fixed them, we couldn't tell any difference. You know, but if you get too far out of line, it might be better when it's revved up, but then it shakes all the gauges out of the dashboard at low speed. So.
One thing you want to introduce here, though, I keep talking about personality of engine types. You know, you hit on a couple of different engines right there, but also the difference between normally aspirated and, in this case, boosted. Well, Tim, you're on that side of that deal. You put a lot of boost up there on the blowers. But interesting enough, and I was going to use a top fuel application, when they're in overlap, that piston rod assembly now is sitting there with a force north of 16,000 pounds trying to get that piston to leave. However, they have an offset to that, and it's called boost. The blower helps dampen that transition. Normally aspirated on it says, hey, just let me out. So rod failures come from mostly an intrusive component. In other words, something got in the way of its travel, a valve, you know, or something like this. But when they do break, there's a reason. And the key is to understand why. So does balance make that difference? That's not what's causing. There's a failure mechanically somewhere else that caused that failure. But the truth of the matter is you have to understand a boosted application like top fuel, what is the amount of boost you're setting into the engine?
Well, it depends on the camshaft, of course, but it'll have 60 pounds, you know,
Okay.
and the light's at 8,300.
Yeah. So what happens there is you have a dampening device. As that piston is trying to leave, it's still pressurizing the cylinder through boost. So it's a dampening event.
Yeah, it's got a tremendous amount of problem in overlap cycle, just like you said. That's why you got fire out the pipe 6 foot tall, right? So, but it's a different motor than this is like FaceTime and Stevie Wonder for me to be up here with these guys. By the way, everybody. So I'm in good company up here. I enjoy this, but I've learned a lot just sitting here.
Fasteners.
To follow up to when you have valve overlap, both valves are open, and you're blowing air through the hole combustion out resuming, you've got 60 psi pushing down on
Yeah, it's crazy. That's what I mean. That thing's good. We got camshafts that's got 72, 74 degrees of overlap in them. So,
that is a damper, right?
yeah.
Yeah, exactly. Which is why you see the fire coming out the pipes at all times.
Right.
Which is entertaining. It's a lot of fun.
And we have, on the big engines that are NA motors, we have none. There's
Yeah,
nothing to help.
exactly.
So it's got, you know, I think each rod cap sees 25,000 pounds of pull,
Right.
you know, so it's pulling pretty hard, and it's dying to keep going.
Yeah. Well, that's it. You know, I want to constantly reiterate the fact that what you're doing today, you're going to do more tomorrow. You're abusing the heck out of stuff. So if you think, I mean, you can go to church on Wednesdays and Sundays, I hope, or you can start using a little engineering and start talking to guys that are really sharp at this and find out what materials and processes need to be changed in order to make that thing live. That is your real challenge right there. You see a lot of different evolutions of engine materials, aluminum blocks, cast blocks. Now, Tim, you're all aluminum. You know?
Yeah, my stuff's all the same junk. I mean, these guys build a really neat block, by the way. We've just been introduced to it lately, and listening to him talk about fasteners has really educated me a little bit more here, even today, because we do exactly what you just said. I needed to stand up and wave my arms instead of just raise my hand when you talked about that. But we use a lot of peanut butter. But,
The only person in here that didn't raise their hand is a liar.
yeah, well, that's right. Well, you know, I mean, that's the way it goes, right? But he's got really good points on the way he fastens things, and we actually have every kind of block available. One of John Force's employees are sitting right out there, and we have one of John Force's blocks, and we have one of his, and we have one of AJ's, and we have one of DSR's, and I do that on purpose because I'm nosy, right? So I need to know why crap happens. It drives me crazy to have this motor come back and things be wrong. So anyway, I really enjoy that part of it. But our motors are so much different than what John builds. His are pieces of art, and ours are just big, giant diesels. I mean, they're just big piece of junk when we get done with them, right? So, but the goal is to get the thing to the end, and like you said, have the rod still hooked to the pistons. You know, we can't live without Dan. His parts are spectacular for our kind of applications, and you know, he builds a ring just for us because the problems that we have. But it is a different education, and no doubt about it.
All right, any questions?
I got another one for you, Randy, but while I'm asking you, if I could get Kevin to bring up the picture with the rod cap moving.
You're on the main, okay, stand back, all right.
But you talked about cheeks on a crankshaft. You said there was 3 cheeks on the outside, and that somehow the torsion on that crankshaft wasn't right, and so they went from a 6-cheek to an 8-cheek crankshaft.
Mm-hmm.
And that still wasn't correct. And so are you telling us as end users, we need to tell the crankshaft designer where to put counterweight on a crankshaft?
No, I wouldn't say that because I think that's outside your scope. Okay, no. What I am saying is you need to talk to engineering about your application. In other words, I'm building a nostalgia car, you know, for a guy that's just going to drive to 7-Eleven. I don't care. You know, you can put a cookie cutter piece in there. But now you're going to sit there and you're going to run Le Mans, right? And this is a durability dynamic at varied RPMs, but nonetheless mostly consistent. No, you have to get at the sweet spot.
You're advocating to talk with the engineer.
Oh, absolutely.
Design it. It's not incumbent on us to tell him where to put cheeks on a crankshaft.
The bottom line is that every engine has its own personality. I always get in trouble when I say this. All women are the same, right? Not going to work. Not going to work. So you got to appreciate the engine uniqueness means that we have compression ratios, we have materials that we use. You know, we're running different temperatures. If you're running high turbo applications, God forgive if you're going to sit there and run nitro. I mean, you better have a big wallet. You know, so the point being is, if you think that engines are cookie cutters, those days are over. You know, what my favorite saying is that this is not your father's Oldsmobile. Forget it. Don't try and go back there because you're just not going to get results. Now, is this what you're looking for here?
Exactly. And Kevin, I would say, if I looked at that, I would say the person that designed that cap and fastener system missed the mark. Because you don't have enough preload on those bolts. The bolts themselves, as I understand it, correct me if I'm wrong, should not feel any cyclic load whatsoever. Because we don't want the bolt to fail on the feet.
Yeah, that is
Go ahead.
correct. I mean,
Find what you want.
you know,
So in that case, the bolts are being cycled, so there's not enough preload.
there's not enough preload, that's correct. Yeah, I mean, you know, looking at like a top fuel application, I mean, we're using you only have so much real estate to work with in the main web. I mean, it becomes a trade-off for parent material versus the fastener. So that's why we have to go to higher strength
Right.
fasteners. So, you know, our inner studs are a custom-made 625. Tim, I mean, you probably torque those to 140, 150 pounds.
Yeah, 175, some of them, yeah.
We recommend 140 or 150, but
Right.
more is always better.
Depends on whose it is, right? They all have a little bit different specs. Your lube has really got me thinking. So me and you got to talk.
We need to have some more conversation.
Yeah, we do. That's interesting.
But, so we are using, you know, on a custom age and inner stud, you know, it's 29,000, 30,000 pounds of plant force. So yeah, I mean, if you're experiencing this problem, there's bad things happening. You don't have the right
That's
fastener.
incorrect with design.
Right.
You made the entire block though.
I've known each other for 30 years, right? You know the world I came from. You know, I was the manufacturer of blocks. You know, I'm going back to the, you know, the early days, the late 80s, working for Dick Maskin.
Maskins, yeah.
You know, we went through the whole evolution.
What I'm saying is your fasteners, if you're putting it into another block, not your block,
Correct.
you take into consideration what it's going into, not just make your fastener right.
Absolutely, yeah, I mean, you know, one of the first things I did, you know, at P1 was to, you know, reach out to the manufacturers, you know, and create some strategic, you know, relationships, because, you know, we've all been in this industry, you know, all of us have been in the industry as long as we have, you know, everybody knows everybody, and, you know, for our product line to be successful, and theirs to be successful, we gotta work together in developing that system. You know, I mean, if you go out into the, you know, into the halls here, and you look at the majority of the billet manufacturers, the majority of the cast block manufacturers, I mean, you're gonna find P1 fasteners in there, because, you know, I could relate with what their, you know, their issues were, and work with them on it, you know, and educate them. I mean, I wish I knew 20 years ago, 30 years ago, what I know today about fasteners, and I'm still learning.
I got a question.
There you go.
Can we do that? I have a question for, we had an engine that, big inch press up motor. It's got a 3/4 inch long crank bolt. It's about 10 inches long, goes through all the pulleys and stuff. Anyway, we broke it off in the crank. It goes way back into the crank by the mains. And my question is, you know, we're trying to find a stud or something to put in there, but when you have a bolt that's like got maybe 10 inches between where the threads are and where the nut is, do you think it ever gets a rhythm to it? Do you think the harmonics is what broke it? Like it's going like a banjo string? Or, I mean, it's got a lot of back and forth torque too, because it's the front of the crank and it's got a balancer and it's tightening all that stuff down. Do you think it would help any if it was dampened in the middle somewhere?
Yeah, we've actually made
Yep,
some.
perfect.
We made some fasteners that actually have some dampener designs in them. Not a part that we manufacture for ourselves currently.
Interesting, yeah.
You know, we have made parts, you know, specifically for customers that are trying to do that.
Okay.
You know, and the other thing, in the Coyote engine, we do a part for one of our customers because it's a situation where it gets a lot of walk, if you will, in the cranks now.
Yeah.
You know, so they've not only beefed up the fastener, but, you know, create a washer that kind of holds it in place that keeps it, limits the travel.
All right. I got one more question and then I'm done. For Tim. Okay, so you're driving this car. When you make a run in that car, are you wishing it would be quicker or are you wishing it'd be over with? You know what I mean? When you're halfway down, are you wishing, come on, let's go?
No, you're wishing for the best run, of course, right? No.
Yeah, but
I think once you drive these cars, the fear goes away pretty quick. You decide whether you like it or you don't, right?
Okay.
Like my kid drove this year for the first time.
Yeah.
And he literally, I've got a dozen people that licenses in these cars, maybe more. Him and one other guy is the only two people that I could ever get out of the car and they could tell you what happened. The other people were passengers, just like you said. That's a passenger, right? So we go through that transition, but no, he could tell you the difference between going 280 mile an hour at half track and 290 mile an hour at half track, and I was amazed at that. Yeah, he'll get on the radio after, he'll have the shoots out and he'll go, Dad, that was really fast. There's some adjectives in there, but you know, it was exciting. But those cars are, you know, these guys make a point about the crankshafts and harmonics and all the crazy crap that happens. And we actually have, in a 4-second run, the main nut will be laying in the bottom of the oil pan. And I'm like, how in the hell does that happen? Right? I mean, it drives me crazy. That's why I try to get everyone's block and go, is it the block? Is it the way I'm putting the fastener on? Is it the way I'm putting the stud in the block? What am I doing wrong? Is it the crankshaft balance? I sent him a crankshaft the other day. I was so mad. I mean, I actually sent Randy a crankshaft, and I said, I put this crankshaft on my balancer, and it walks across the room. So what am I doing wrong, right? So all this is education to me also. So bless you guys for letting me sit in on your, and I'm just hoping I trickle some of your intelligence into my thought process at the end of the day. But these cars are so different than what you do, John. You know, I mean, it's just a little rolling bomb, but it still has to be happy. You talk about the harmonics, and we see that so bad. We got a 60-pound clutch hanging on the back of our crankshaft, right? So it hates that. The crank breaks in the same spot every time. We have carbides in the back of the flywheels that hit the back of the motor plate so the crankshaft don't break, and so the rear main don't fall out. And if you lose that by 10 thousandths between the carbide and the motor plate, then the rear main's junk after one run. And it's just the stupidest thing you've ever seen. But a lot of it's the problems that you guys have talked about here in the last hour. It really is, I think. The more I listen, the more I think I'm dumber than I really thought I was. A lot dumber. But it's a whole different animal than what you do. Yeah. Well, I always say that. People go, well, look how beat up it is. And I said, hell, it just took too long to get there. If I got there faster, it wouldn't be beat up at all, right? So we make it go faster.
Well, you know, one of the things you guys do is you're constantly evolving. What you do is insane. I'll just put it bluntly. I used to bark at the 410 guys, and those guys are entertaining as hell. But you're just borderline nuts. You know, what do you do? But anyhow, the bottom line is that evolution. Mark Oswald, friend of ours, right? We're out in Seattle, and we talked about things just on what you're talking about. Yeah. And we took a look at his flywheel, and they showed me all the renditions. We talked about it and said, look, here's what my thoughts are, right? Now, since that time, they have adopted a couple of things, and it's about increasing mass, believe it or not. And this whole thing, drag racing specifically, light is good, those days are gone, all right? Integrity is key, all right? And you can't do it with a little teeny tiny part. Those days are over. Now, Antron just sat there and pulled the rabbit out of the hat and got another championship. Yeah. Impressed. Every one of you guys continue to evolve every single race. I always see new avenues of change, and you're not afraid to try. You know, that's the part that's really, but that's also within this whole group here. But I want to stop here for a second because I got the cup guy here, and I also got the bearing guy here. I want you to pick up on what we just talked about here.
Yeah, I thought about the question that was made about the bolt stretch that was coming down. There's multiple ways. There's multiple ways that a cap can move. You know, in this case, we have bolt stretch going on. A year ago, Cass showed sitting right here. We did a joint thing together. He kind of threw me under the bus, but somehow I managed to survive at the PR convention about flex. And Cass sent me a picture, and it was caps that were flexing this way in the middle. And as we started talking about it a little bit more, and it was rod failures is really what Cass was talking about on a diesel. And I saw cap flex where the fretting was wedge shape. So you could tell it wasn't stretching bolts. The whole cap was flexing. I was privileged to see some FEA animation from Alan Johnson on his block, and it was disturbing to see that Tim's strapping in behind this block that's sitting there going, oh, dude, you're more nuts than I thought. But sometimes we don't know how that's flexing. It can change in application. As Cass and I chatted this out a little bit more, it was a newer application, and it was because of lightning holes in the block by OE. You know, they do that to meet the CAFE standards. So, you know, you get that engine, correct me if I'm wrong on anything on this, Cass, you get that block to rebuild and you're going to do something, you know, you're limited to how to maintain because the integrity of the block. CAFE standards keep saying light, because the OEs have to, our politicians are telling the manufacturers of how to do it. That's why we, as MALA, is already testing OE for vehicles that will be coming out 5 years from now, right? And they lighten stuff up, so we're working on new materials and new parameters within the parameters that the OE has given us to meet the government officials' CAFE standards of what's coming out. So now we add boost to it, we add nitro, pick your poison, and so a flex in here, in this case, it's animating bolt stretch, right? We can have cap flex. You see a cap broken in the middle. Which way is that cap going? I don't know. Sometimes the fretting tells the story. I always say parts don't lie. It's just knowing what they're telling you, right? So that's why we're all here, is to learn from people at this whole event.
So the nutshell of this is, if you can't capture how old and maintain, it's gonna break, right? We got some really smart guys up here. These guys know what it takes to have good tenure, different expertise in different arenas, but each one of them has a unique project. And for instance, I'm gonna go back to the 410 group for a second. See, they don't run a damper at all. And my hair goes right, standing straight up when I hear that. But they do it because the gyroscopic effect, they're out there full throttle and they just sling this thing. I'm gonna let you tell the driving story, I think. But the bottom line is that damper that's out there says, no, we're not turning. We're going that way. And the driver's saying, I can feel the difference. True or not true?
No, there's no doubt about it.
So when I talk to you guys and I ask for, you realize this crank is gonna break, and you say, as long as I win the race, right? Pretty much. So, but you've also gotten a lot wiser, and materials and processes have changed to support that. But at the end of the day, you can't have application. This is what I'm saying. Drag racer, 4 seconds. Well, that's a slow run, come to think of it. You're.
We used to say you have 4 seconds of your undivided attention when you're driving. 4 seconds of your undivided attention.
Whereas these guys are out there. What is the typical lap run time overall?
I mean, it obviously depends on, track size, but I mean, you're in a 12-second range.
Sure. So, but they're going up and down cycle, up and down cycle. That crank is doing this and this and this and this and this. All right.
That's a half mile, yeah.
Fair enough. Yeah, that's right. Yeah. So this foot's moving a lot, right? But the point is, it's very entertaining, and I love it. And as long as I don't sit up against the net, you guys throw dirt at me every time. But the point is that it's a unique process. So whatever your field of expertise is, whatever your client base is, understand it is a system dictated process. You can't be building a drag race engine for an endurance application. Yes, there's common cranks go round and round, pistons go up and down, but I'm telling you, two different animals. And with the Cup guys, now that was one of the things, it used to be when you built engines back then, it had to go 501 miles, right? That's all it was intended to, there it is. Where are you at now?
Yeah, about 5 years before the multi-race engine came out, I was looking at parts. It took us 5 years to get to the point where we would run a Cup engine twice. Ran AVL tests, now you're looking, you want the engine 1,400 miles, but the key is you want it to make the same horsepower at 1,400, because guess what? How much horsepower you have when the checkered rag waves is where you're going to win or lose, right? So the thing is, we come back, we were, sorry, not there anymore, but we were looking for minute percentages of change, and we got to a point at 1,400 miles, the engines were better than when they left. Small, but we'll keep that. That's success. So, and that goes into oils and, technology, fasteners, keeping everything maintained, harmonics. One of the things I was very fortunate with, got to work with Ford, where we actually encoded a dampener and worked on dampener to the track based off of what RPM curves you were running in to figure out which order of you were maintaining that RPM the most at to dampen the O-rings in the dampener and the mass weight to achieve optimum at specific tracks. So we would change our dampeners to different tracks based off of the low and high RPMs that we were peaking the most cycle times at those RPMs.
One thing I want to introduce about dampers, and that is there's a couple of different processes out there, and I'm not going to support anyone as saying one over the other. However, they are application specific again. So, but I do make this statement about all dampers. And from the day you put it on, it's not like wine, they don't get better over time. They degrade instantly and to a higher level depending upon the aggravation that they see. So when you buy that cookie cutter part number from a resource that's for this engine type, I'm probably going to say there's a better than 50-50 chance, and probably more like 60-40, it's misapplied to the application. So once the damper becomes ineffective, you just got dead weight hanging on an engine. So you really need to go back and talk to engineering, right? The parts guy, the sales guy, there's a place for them, I get it. But if you're really talking about an application that is specific, there is no cookie cutter part. You have to pay the price to get the right part to get the net benefit. I want to go back to Cass's story also, because we've changed materials. The old standard cast iron block, well, we changed those materials, and in doing so, it has the merit of structure, right? They say it's stronger so we can lighten it. That engineer went to sleep at the helm. They just simply didn't understand the power of frequency. And with the diesel, let's be fair about it, they are a little bit more rough than the Honda, okay? In fact, I always tell people that one of my favorite questions that are presented to me about balancing, like motorcycles, Harleys, people call and say, what's the magic formula for Harleys? And so I studied this for years, and I came to the final conclusion, it's called buy a Honda.
Yeah, exactly. Get rid of a Harley.
So you want to remember, there are certain things you just can't get there. That's all there is to it. You can wish it, you can pray for it, you can do anything you want. But numbers don't lie, period.
I just wanted to say I really appreciate these guys. I hope all you guys do too, because I started out in the gas station business. That's what I did, and ended up with a machine shop because of my top fuel car. And I couldn't afford to send my box out and had them fixed. And so I thought, well, the only way to do this is to figure it out myself. Well, in the meantime, of course, then you gain customers, right? Well, we stopped building circle track motors because you need to give them a roll of tape when you give them motors so they can put it over the gauges, right? So because they don't look. So it just gets ridiculous one time after another. So if all you guys have machine shops out there, I'm very impressed with how you live and breathe through the machine shop business, because I've had one for 25 years, and it's the hardest job I've ever seen, because like Randy said, there's no application the same. There's no customer the same. Every one of them needs educated, right? I mean, you hand it to them in perfect condition, and they'll bring it back and tell you that it was broke. So God bless all of you for doing that, because it's really hard. I would never dream it'd be that hard to do this, but it is. It's tremendously hard. So, and John especially, he does a lot of neat stuff here, and we're lucky just to work on the junk that we work on, and truthfully, my machine shop does mostly diesel work just because of that, because those guys have money and they need their stuff fixed. So, and that's what I do more than anything. But I love all this fastener stuff and how it works and how it means everything. And Randy's points are, you should really take them to point, because they're spot on, because no one's application's the same. All your customers are different, and you got to be able to think outside. You got to outsmart your customer. Really, don't you think, Randy?
Yeah. Well, thank you. The check's in the mail, by the way.
Yeah.
So.
Well, I'm just being serious.
Bad joke. All right. Any questions? How are we doing? Now's the time, guys. Cast shows.
Quick question, and also something to add, that I don't think there's probably a better example of what you guys are talking about than anybody that's ever ran a lathe. And the reason for that is it's the increased flow. It's basically the same thing as the tool nose radius, if anybody knows what an insert is. The amount of chatter and deflection from the bar that we're using, it's direct relationship to surface finish that we're going to achieve, right? But we have, you're talking about frequency. Spindle speed variation is something that keeps it guessing all the time, because it never locks on
Right.
to a certain frequency.
Right.
I've used bars before that, Ken Metal would come out and would run it, and it's just horrific. It got to the point where actually a 1 1/4 inch bar, he continued to run it and snapped the bar, just broke it off.
Right.
While it was in the cut. The interesting thing though that I wanted to add about that is the tunable boring bar. So the question would be, the material that is used, obviously everybody's using heavy metal, mallory.
Mhm.
How much relationship to frequency, the material that you're adding is going to affect the frequency that we're seeing in the crankshaft? Is that something that?
No, great question, because one of the things that we got to understand, a material differential has different frequency response rates. So a crank, and I'm just, take a good high quality crank, whatever material, you can name it whatever you want. But then I put in a bolt-on counterweight that's made out of tungsten. Tungsten is a power metal. Well, I can change that recipe just like a cake mix. As such, I can actually use it in a double fashion. And I told you, a counterweight is a dampening device in its own right. But now, within the crank, I can have 2 different frequencies, which will help nullify. Or, and here's the issue, it can go the other way, all right? In other words, I don't like the word guess because that's bad, but you can sit there and just ping the unit and find its natural frequency. And then when you see disparity of the two, then you have to mate and decide where it's going to run in that realm, and it'll either have an advantage or disadvantage. But here's what I give it automatically. The fact that it's different has what we call an interruption or an interference that will help and assist in cancellation. Most of your boring bars you talk about on the lathe, they have tungsten in there. They have a floating weight. And that mission is to hit frequency cancellation. That is the key to those bars. So I'm big on bolt-on counterweights. Big.
Does Caterpillar on 36 irons, are they running any counterweights that are used with the material versus apparently?
Well, I'm going to merge two companies. I did it with Cummins also. In Cummins, we actually made tungsten bolt-on weights. Two things happened there. We lowered the polar moment of the unit because it was so much smaller in diameter, which was a key advantage, except that it was a diesel. There makes so much other disruptive forces, the merits of it were not really beneficial, right? But the Caterpillar guys, or a lot of the bolt-on, the Waukesha's, things like this, they're typically mated similar materials, but they also typically have a much lower band or a RPM band, so they don't have that, whereas we talked about engines of 12,000 RPM now, not unreasonable. That's a pretty big window, right? The key, though, is if you find it, there's only one remedy. Get the hell out of it. Do not stay there. I heard a comment, you leave something hostile long enough, it'll break. Get outside of it and you have a chance. It might still break, but it's already fatigued out. And one of the things the natural frequency do, they will fatigue any material, guaranteed, okay? Any add to that? Are we good? Kevin? Anything else? Yes, sir.
So how does the weight and location of oil within a running engine affect the balance and harmonics?
Actually, it's a really interesting question because the only way to resolve that is with a lot of beer. The only way that's ever worked, in other words, people always ask me, how much do I say? I can do the math equation for you, tell what the clearance surface area, the length from the primary feed. I can do all that, all right? And then this guy comes along and says, no, you got 71% air, so that went to hell. Now, the point being is that we go through this. I always tell people I give a generic window. Now, back in the day, I'm trying to think of the guy who was in Virginia, Sonny Leonard, right? He bought a machine from us. This goes back 20-some years ago. And I said, Sonny asked that question, what do we do? I said, well, it's here to here. And I said, it's discretionary. He said, fine, I'll use 0. I said, you can't use 0. He says, well, what's yours? So the point is, drink enough beer, last man standing wins. Fair enough? Okay. Another question? Yes, sir. Yeah, sure.
It seems like there's some really big holes with very thin walls, and it seems in high-end cranks. So is there not a torsional rigidity problem in the pin with these rods?
There's a legitimate argument in what you're saying, and I sort of barked about that earlier. You can't take a counterweight and make it lighter and make it stronger. In other words, drill it, right? But you can gun drill a unit, and you can go ahead and do certain machining techniques that will make tubular effect better than a solid, right? But the primary reason that's done is so that they don't have enough counterweight mass, and so they have to go to the other end and change that perspective. That's why it's done. But let's go back to a couple things. The oil holes that we talked about here, the fact that we've been able to minimize their diameters, we used to, remember the big block Chevys that had the cross drill and those things? I mean, my God, you could drink out of the thing. They're horrendous. Well,
427 had 16 grams of oil in the drum.
there you go. All right. So, and again, so there's another variable, but here's my point. That weakened that crank. And when you get strokers, we get there, you leave that oil hole big, I guarantee you there's a thin wall. And what you've done is you put a stress point in there. So the crack, believe it or not, starts there, not necessarily on the surface of the crank. When we mag them and you go down into the bore, you'll see this generation of the cracks via the oil hole. So I want to go back and simply say it's done because there's not enough within the crank bay area. That's the other side of it. If you were going to be able to increase the crank bay area, that screws up everything north of that. Cylinder head, camshaft locations, so it's just a giant change. Whenever we went to a spread bore, we started going, spreading from cylinder to cylinder. That and on created this chaos. But when you try to change that displacement of the crank bay, this is why, by the way, heavy metal works. That now we reduce that whole network. We don't have to have that tall block. So my point is this. I want to go back to the oil hole specifically. If it can be restricted just because what he said, we were at 71%. Okay, air is compressible. You don't want air in your feed line. Can you get 100%? I don't think so. I think there's going to be some dynamic there. But you certainly don't want to run 70% plus. Now, does that answer the question, or I missed the question altogether? I've done that before, by the way.
So we're in a class where we've got it old stuff, got to use stock crank. So you can modify them, but you can't go to a bespoke aftermarket crank.
You can't get caught with it, is what you mean.
Trying to reduce lighter costs.
Yeah.
Lighter block, lighter piston, lighter ring package, lighter everything reciprocated, but how do we reduce the weight of the crank? What's the best way to do that? It seems like taking weight out of the pin end is a pretty good thing.
Go ahead.
So I'm gonna add a little bit to that from crank guy to a bearing guy. So when you, based off power levels you have, you actually can have a crank where the pin starts to ovalize. Okay, from the force to pin. If it's too light in the pin end,
Right.
it will start to ovalize. So now that's affecting your clearance from your bearing to the crank because now you're no longer round. I have some slides, I did some presentations, they were not today, but I can show you bearing ovalization from polishing or grinding chatter where that lobing effect creates film pressure spikes because it's acting as an eccentric. So it's spiking the film pressure. When it spikes the film pressure, immediately after that, it's low film thickness, which is where your contact, as I demonstrated on there. So to your point, I can't tell you what that answer is. It depends on, these you guys would have different answers based off the application, okay? But I can tell you the pin will ovalize if it gets too big, not enough cross-section in there, or the location of where it's at. You want to lighten it? At what point do you fall over that edge?
You know, we had crankshaft manufacturers that would take the last journal based on what you said, and they gotta make it wider, right, because we can't get it up, we got 3,000 file blades, stupid crap. So they take the last journal and try to make it too small. Well, exactly what you said happened. I've started seeing spot faces on my bearings, first
Yep.
off, on, 2 and 11.
Yeah.
And then I see cracks start going down the oil hole. I'm like, why did you do that? Well, we couldn't get the thing to balance well, so now they're tapering. And just a hair, but it made all difference in the world. You lose that oval.
You're changing the direction of the force
Yeah.
by
Yeah.
tapering versus
You lose all that oval.
In fact, on the top fuel units, during that period, I remember being in your facility and I looked at the rod journal and you could see what we called it sort of a grayish area linear across the journal. And that's what that is. It's a friction response. It gets so hot, right, that it actually, the carbon molecule is drawn to that area. That's how hot it gets. Now, wait a minute, it's still running an oil bath. No, you got to understand, especially with the power making that these guys make, that's an unusual gig. But my point is, like Dan's always said, look at the part, it'll tell the story. You just got to know what you're looking at. And so to make too big of a lightning hole, bad idea. But it's driven by the fact that they typically cannot put enough counterweight economically. So the mission statement would be Mallory. Well, the cost of sales went up. So a lot of everything, even the 6 counterweights when they were originally generated, 8 counterweights was rule number 1 back then. The bean counters got in and say, I'm not going to pay for that. Figure another way. So they put a 17.5-degree pitch to it. Well, it worked. But it was in the era of 3,000, 5,000 RPM, 100, 200 horsepower. That deal's gone. Okay? Any questions? Yes, sir.
Always go to tighter bearing clearances. Is there any
You open up a can of worms.
Yeah, that's a whole nother topic for another session, but definitely yes. It goes back to, again, the CAFE standards. So, thinner oil, I'm hearing zero weight oil is on the horizon. I mean, you won't know the difference between the water you drink and the oil you put in the engine.
I sell it right now.
Do you? Okay, there we go, right there.
Already sell it.
Okay, so, yes, because again, pressure is the resistance of flow. So the thinner the oil is, the less film pressure you put on there. So to restrict that, you have to tighten the clearance to make that restriction of a thinner moving. So, a good rule of thumb or these guys, 1,000ths per inch of shaft is correct in most cases. That's not the case in that application. It's going to get tighter and tighter.
It's very important you understand that is a trend coming that you can't stop. Get that clear. And in fact, what is it, the little V6 that Ford has, the journals are crowned. They're not flat. Now, the premise behind that is that once it comes to operating temperature and standard load, it flattens out. Think that one through for a while.
Yeah, and one of the reasons it's crowned is because the block itself is moving. So it can move because that's how they fix it.
When we take those engines apart, as far as I'm concerned, they're a paperweight. I wouldn't bother playing with those engines for love, money, or sex. Well, maybe sex. But the point is, you got to appreciate that this is what's headed your way. You got to learn to address it, and I keep harping the personality dynamic. If you're going to be successful, you got to understand this is not a cookie cutter anymore. This is application specific. Now, stay with the old premise. I'm going to give you a recipe for your own demise. All right? Any other questions? Yes, sir.
In your illustrations, the difference between all of your torque specs, if you have the angle in which the fastener moves, is there a reason that you don't supply angling instead of torque specs? Is that something silly I'm missing?
Well, that's a great question, and that's a direction that we would like to head. It gets a little bit more complicated when you're talking about a solid joint, which is what I was sharing data. It's straightforward, because it's just a measurement of displacement. You get into a head stud application, a head bolt application. Now you got a gasket. Torque angle becomes a little bit more of a consideration because you got another variable involved, but. The last slide there, we said there's future discussion because torque angle, it is, the most accurate way to know you're getting a proper stretch. You're measuring the displacement. It's, again, going back to the spring theory.
Yeah. But keep in mind the process to get there is the one thing if anything they leave today, this guy's gave you a golden nugget to improve everything that you do. What you think you were doing probably is what you were doing. Fair enough?
Yeah, just to add to that, if you look at statistically, using torque simply as an input, you're talking plus or minus 20-25%, of accuracy. You look at torque angle, you're getting your accuracy, 10% or less.
Torque angle starts with amount of torque. It's like they torque it like 40 pounds.
Yeah, you've got to get to everybody uses a little bit different term, but you got to get to a set. You got to start somewhere to, lack of a better term, get the slack out of the fastener. Everything gets seated, and then you measure displacement from that point.
Believe it, it's easier to do.
It's gotten a lot easier. Back in the day, the first set of connecting rods, it was a set of Oliver rods, and they, all they gave me was torque angle, and we had those snap-on gauges with the, little finger, and then it's like, gosh, did the finger slip? Did I get the angle right? And it was frustrating. But today, torque angle with the
Say 60 degrees, it's too flat.
yeah.
All right, how about it, guys? Come on. Got another one? There we go.
So we get an engine in, we tear it down and rebuild it, and we pull the rod bolts out, small block Chevy raised engine. We're gonna work and stretch that rod bolt to hone that rod, take that rod back
again, going back to accuracy, stretch is the way to measure it. I mean, torque, torque is in tension. Torque is just it's a way to create tension, but now you've got the friction factor in there. I mean, if you can measure the stretch of the fastener, I mean, that's the answer. And going back to the original question, people get a little confused about yield. There's a proportional limit when you're torquing a fastener. And you are, when you're stretching the part, you're yielding it, okay? But going back to Hooke's law, you're keeping it within the elastic range of that material. And that's all determined on, the UTS of the material, the diameter. There's a lot of factors involved in it, but as long as you keep it within that elastic range, you don't have permanent deformation of the part. If you exceed that, then you got a problem. Then you need to discard the fastener.
So I got a question. How do you know when you've arrived at that status?
Well, that's
Yeah.
that's another good question.
Yeah.
Yeah. On rod bolts, I say everybody, but most engine builders are accustomed to that. They're logging, the lengths of their rod bolts, before and after, so you've got data. That's the problem when you start looking at studs and bolts and another can of worms, not to open up here, but getting into torque to yield fasteners. I mean, that's a whole nother topic in itself. I mean, everybody asks me, can you reuse torque to yield fasteners? And, my answer is maybe. I mean, if you know what it was torqued the first time and what the length was, and if it's within that elastic, your proportional limit range, sure, you can. But
By definition, you're outside that. By definition. If you do torque to yield, and you're going beyond yield, you're beyond the proportional limit.
maybe.
Maybe. Yeah.
Maybe. I mean, it all depends on the fastener design. I mean,
Yes, sir.
I've had to your point of torque to yield. Back in the day when we had the escorts to work on, and I had one customer absolutely refuse to buy new head bolts, and probably 95 out of 100 times it was fine using the old ones, and he would charge for new ones. And he, you know what? I made so much money by charging for stuff I didn't sell. I can eat a job or two, but the point being, yeah, most of the time I guess they're going to work again. And that's in an engine that's been overheated and the head came off for a reason, not for maintenance. Normally it would crack so you were smoking hot already. So you had the heat aspect of it on the bolts as well. And most of the time you got away with it. So, yeah, probably.
I mean, the strategy with torque to yield, and I think a lot of people don't necessarily understand it from the OE perspective, is it's given them a big range to get that fastener torqued in production in a timely manner. I mean, they don't have to hit an exact number. They can use a less expensive material. They can put it into yield to get more clamp force, and the window is just a lot bigger. There's a lot of things that they do in the OE applications that, people kind of overthink of why it's being done. I go back to the old small block Chevy manifolds. They changed the angle of the bolt hole right by the carburetor pad, and everybody's like, oh, it's a better sealing strategy, and I'm like, no, man, they had to get an impact in there on the assembly line, to shave a fraction of a second. And same thing goes for fasteners. You look at a lot of the OE fasteners today, you look at the pitch diameter. I mean, we've got pitch diameters of 1.5, 2.0. It's all about speed of installing those fasteners in production. And, it can work to your disadvantage. Like the slide Randy showed, well, it's right up there on the screen. We've seen application where you get a real steep pitch angle, 2.0, and you get in an endurance application, the mechanical advantage works against you. I mean, it helped them on the OE to install it, but, in an endurance application, you get into a harmonic situation, it's a mechanical advantage to let it come out.
So, piggybacking on what you just said, how much does the K factor, is it affected by the pitch diameter, by the tolerance of the bolt, and by well, just based off the pitch diameter and the tolerance of the threads?
I mean, those are obviously two key factors involved in the K factor. You know, also the surface finish of the thread. You know, is it a cut thread? Is it a formed thread? You know, the material, when it's rolled, you know, what is the burnish effect on that thread? I mean, that all factors into that K factor. Yep. Yeah, in diameter, I mean, surface area, you know, I mean, if you're talking a 1/4-inch fastener versus a 5/8 fastener, I mean, you know, I put up that equation, I say it's simple math, but when you look at the K factor, it's not so simple then.
Keep in mind, everything we just said there can be totally violated with frequency. I want to keep harping on that because that's a variable that most people, you've told a story about an application where you had a bolt or a stud back out. And of course, told the customer that and he was in denial. Well, I'm not sure how that resolved, but it was probably pretty close to a pissing contest. But you know, the point being is that
Hooke's law is a function of frequency?
Say again?
So you're saying Hooke's law is a function of frequency? Is that what you're saying?
I'm saying there's linkage, okay? Hooke's law is a standalone component. You know, to oversimplify it, if I take an object that is impossible to move, it can't vibrate. However, if I generate enough force and it surrenders, yields, if you will, it always goes into oscillation, right? So that's the spring part of it. That's where Hooke's law really steps in, yeah. So. Listen, those are stories that have been told. You know, how did they get there? Well, there's a reason. Sometimes you just don't understand the cause. All right, anything else? All right, how about any closing comment real quick?
You know, again, thanks everybody for coming. I know we went a little bit over. We always appreciate the questions. It shows that you're paying attention. And my goal is everybody's walking away here learning something today that's going to make you a better engine shop moving forward. So again, thank you. It means a lot to all of us.
Go ahead. Any-